Hello everyone and welcome back to another video. In this video we're going to look at scientific notation as well as comparing accuracy and precision, which is a little bit of a different topic, but they fit well together for the series of videos. With scientific notation, it's very similar to prefixes in that it allows scientists and chemists to communicate and share and calculate very large and very small numbers in a way where you don't make many mistakes. Because if I had to write 1 with 10 zeros, there's a good chance I might mess that up. So instead, maybe I say 1 times 10 to the 10th power. That's always going to be 1 with 10 zeros after it. So this is essentially what scientific notation does for scientists. It makes writing big and small numbers really easy. And the method to figure it out is pretty easy too. There's a couple rules we have to follow. So anytime you have scientific notation, it's best practice that the number you have preceding your power of 10 times 10 to the power of whatever is between 1 and 10. And usually it's not going to be 10 times 10 to the fourth. That's bad practice. It should be 1.0 or 1 times 10 to the fifth if you wanted to, achieve that. So usually it's between 1 and 10. And then you multiply that value between 1 and 10 by 10 to the power of something. And again, the whole purpose of that power of 10 is to move the decimal a certain number of directions. So you'll look at these two numbers here, and the scientific notation looks really similar. It's 5.5 times 10 to some power, but the numbers are drastically different. And that's because of the effect a negative exponent versus a positive exponent have. A positive exponent indicates that the number is much larger than 10. A negative exponent indicates that you have a very small number, a number that's much smaller than 10. Now, I'm sure in some of your math classes previous, and possibly other science classes previous, you learned some sort of rule that, for example, if it's a positive exponent, I'm going to move the decimal that many places to the right. If it's a negative exponent, I'm going to move that many places to the left. That's one way to do it. I think the easier way to do it is to kind of recognize the mathematics that you're actually doing there and kind of recognizing, how it makes sense. So let's look at this, for example. I want to turn 55,000 into scientific notation. Well, how do I know this is correct? How do I know this equivalent statement here is accurate? Let's look at it. Let's say I have 55,000. I need to make sure this number gets between 1 and 10. Well, how do I do that? I have to move the decimal so many places to get it between 1 and 10. If I move it to the right, is that going to make it between 1 and 10? No, it's going to make the number larger and larger and larger, and I'll never seek to reach that goal of having it between 1 and 10. So that means I have to move it to the left. So I move it 1, 2, 3, 4 places to the left. Now, the number I have here is 5.5, which is great. So 5.5 times 10 to the power of 4, because I moved it 4 places. Now, the next thing I have to ask myself, is that 4 positive or is that 4 negative? And this is where people memorize to the left is, bigger, smaller, whatever it is. Really, what you want to think about is what you're actually doing here with this math. If I were to take 5.5, what would I have to multiply it by to get me 55,000? I'd have to multiply it by 10,000, right? 1 with 4 zeros after it. So by a positive exponent, I know it's going to give me a bigger number. I'm going to leave it at 5.5 times 10 to the 4th power. And I'll have the correct scientific notation. Because I know positive exponents, large number, right? Let's look at the inverse of this. Let's say I'm given 5.5 times to the negative 5th, and I have to convert it to regular notation. Well, I have 5.5. I have to move the decimal 5 places. If I move it to the left, the number is going to get smaller. If I move it to the right, the number is going to get bigger, right? So if I have a negative exponent, that's indicating to me I have a small number, something that's smaller than 10. I move it to the right, it's going to get bigger than 10, so I got to move it to the left 5 places. So I go 1, 2, 3, 4, 5. So I move it 5 places. I got to add 4 zeros here to make that happen. So it should be 0.0000055. And lo and behold, it's 0.000055. So that's how I know it's correct. Now let's say, for example, you were given 5.5 times 10 to the 0th power. Anything to the 0th power is 1. That doesn't mean the answer is 1, right? That's basically just telling me that it's 5.5 times 1. Because if the power is 0, it's basically telling me I'm not moving the decimal in either direction. So 5.5 times 1 is just 5.5. So that's an easy way to kind of recognize scientific notation. Let's move on to accuracy and precision, because this is huge in science, chemistry, and in many fields. If you go into psychology, you're going to deal with this. If you go into biology, things like that. And often we use this with regards to calibrating our equipment, because if our equipment's giving us precise results but not accurate results, is it really working? And there's certain tweaks that you can make accordingly. So what does it mean when something's accurate and precise? I'm sure you've seen the picture of the dartboard before, right? Accuracy basically means to a chemist that the number is what it should be. So if I calibrate my spectrophotometer for it to give me a certain reading, and if it's accurate, it's going to give me the reading that it should be. Precision then lies when, if I do multiple readings, how close are those readings going to be to one another? So precision is how close the bullets or the darts are to one another. Accuracy is how close are they to the center, right? Do they mean what they should mean? And then precision means, is it replicable? Is it going to give me the same results over and over again? So accurate and precise, they're going to land dead center. It lands where it should be, and they're very close. Precise but not accurate. Notice none of them have hit the bullseye here in the center, but they're clustered together. And then you can have examples where things are not accurate or not precise, where they're kind of spread out. This is somewhat precise, but it might as well not be, because they're pretty spread out. So pretty spread out, not really super precise because they're not really close to one another, and again, they're not accurate. So looking at that, we can do some calculations to determine how far off our measured experimental value is from the actual accepted value. So this is a common calculation you'll have to do in labs to determine how off you are, and we call that the percent error. Here's what this calculation means. It looks really complex, but it's really not. The measured value is the value you got in your lab. So this is the lab value. So when I do an experiment and I use a ruler, or I use a beaker, or I use a graduated cylinder, or I use a scale, whatever instrument gives me, that is the measured. That's what I got. From that measured, I'm going to subtract what the accepted value is, or what the value should be. It's what it should be, or also known as the expected value. So let's say I run the experiment and I predict that it should be 10 grams, for example. But, actually what I got was, we'll say 9.8 grams. Close, but it's not quite what it should be. I would find the difference between these as an absolute value, which is what this is indicating here, because you don't want to have a negative number here. So I would say, okay, the difference is 0.2. That's the difference that would go as your numerator here. The accepted value is what you divide it by. That's your denominator. So you're basically finding the difference, dividing it by what the value should be, and then you're multiplying it by 100. And again, these lines here represent absolute values. So that way it's a positive value at the end. So if I were to take, 0.2 and divide it by 10 and multiply it by 100, that would give me my percent error for that theoretical experiment I just described. Thanks for tuning in.